All right, let's dive into what is basically a scientific detective story. It's all about a massive puzzle right at the heart of physics, and the visionary scientist Carlo Rubbia, who is daring enough to try and solve it. This isn't just about tiny particles. This is a hunt for the fundamental rules that run our entire universe.
So let's just start with the biggest question there is. What actually holds everything together? From the stars way up in the sky to the very atoms that make you. It's all run by a handful of fundamental forces. For decades, physicists had a pretty good handle on most of them, but one force was still a total mystery, with a huge, crucial piece of its puzzle missing.
Okay, so here's the setup. Let's travel back to the mid-20th century. Physicists have this beautiful, elegant theory about how the universe works, but there's a big problem. A huge piece is just gone. And without it, they have no way to prove their theory is right.
At the very center of this puzzle is something called the weak nuclear force. Now, you might not have heard of it. It's not as famous as, say, gravity, but trust me, it is absolutely one of the four essential forces holding our reality together. It's in charge of things like radioactive decay, which is the engine that makes stars shine and forges new elements. So, yeah, it's kind of important.
And here is where it gets really interesting. A groundbreaking theory had managed to weave together electricity, magnetism, and the weak force into this one neat package called the electroweak theory. It predicted that the weak force, just like light, was carried by tiny messenger particles. In this case, they were called the W and Z bosons. The problem? No one had ever seen them. They were basically ghosts in the machine, a giant gaping hole in our understanding of the universe.
So to find these missing pieces, physics needed a new playbook, something bold, something nobody had ever tried before. And that is exactly when our protagonist, the Italian physicist Carlo Rubbia, steps onto the stage with a plan that was, frankly, audacious.
So back in 1976, Rubbia drops this proposal. Now, I know it sounds super technical, but in the world of experimental physics, this was a radical idea. At the time, everyone was thinking we need to build bigger, more expensive machines from the ground up. But Rubbia had this brilliant, counterintuitive idea. He said, let's just transform a machine we already have into something way more powerful.
And here is the absolute genius of his idea. See, the old way of doing things was kind of like throwing a baseball against the wall, a fixed target. You get some energy out of it, but a lot gets wasted. Rubbia's idea, it was like throwing two baseballs at each other at incredible speed. That head-on collision focuses all that power into one tiny spectacular point, creating a burst of energy so immense that he figured it would be enough to actually forge those heavy W and Z bosons out of pure energy.
With the plan in place, the hunt was on, and this was no solo mission, believe me. It turned into one of the most complex and ambitious scientific projects ever attempted, a true global effort to find these incredibly elusive particles. But there was a huge technical problem. If you want a proton-antiproton collision, you first need, well, antiprotons, and you need a lot of them, all flying in a perfect, dense little beam. This is where another hero enters our story, Simon von der Meer. He developed this absolutely brilliant technique called stochastic cooling. The best way to picture it is like trying to gently nudge a scattered, chaotic crowd of people into a single, orderly line. It was a way to wrangle these unruly antimatter particles into the super precise beam they needed. Honestly, without his solution, Rubbia's whole idea would have been impossible.
And the sheer scale of this effort was just immense. We're talking about hundreds of scientists from all over the world. They packed their bags and flocked to CERN in Switzerland to join something called the UA1 collaboration, all led by Rubbia. This was team science on a scale that nobody had really seen before.
So in a nutshell, the hunt followed 5 key steps. First, you have to actually create the antimatter. Second, you use van der Meer's brilliant cooling technique to focus it into a tight beam. Third, you accelerate both the protons and the antiprotons to almost the speed of light inside CERN's superproton synchrotron. Fourth, this is the moment of truth, you smash them together head-on. And then, the final, incredibly difficult step, you have to build a detector that can sift through all that subatomic debris to find the unique signature of a W or a Z boson. So, years of planning, building, and incredible teamwork all came down to this one pivotal moment. The stage was now set for one of the biggest discoveries in the history of modern physics. And the success came stunningly fast. From Rubbia's first proposal in 1976, it only took 7 years for the team to make their big announcement. In 1983, they officially confirmed they had found the W and Z bosons. And get this, the very next year, the Nobel Committee awarded the prize in physics to Carlo Rubbia and Simon van der Meer. That's just an incredible pace.
And just like that, the ghosts in the machine were real. This was so much more than just ticking a couple boxes on a particle checklist. This was the moment that the grand, beautiful idea of the electroweak theory, the idea that two of nature's forces were really one, was confirmed with hard evidence. The standard model of particle physics, our best description of reality, was suddenly standing on solid bedrock.
But this discovery was about so much more than finding two particles. Its impact just rippled through science, through technology, and even through the very way we conduct research. It left behind a profound and lasting legacy.
You can really look at this legacy in a few different ways. Scientifically, it validated a huge cornerstone of the standard model. Technologically, the stuff they had to invent just to make this work pushed accelerator and detector tech way forward. Institutionally, it cemented CERN's reputation as the global leader in particle physics. And maybe most importantly, it set a brand new standard for what these massive international scientific teams could actually achieve when they work together.
And the story doesn't end there, not by a long shot. The technologies and that collaborative spirit pioneered by Rubbia and the UA-1 experiment, they laid the direct groundwork for the next generation, the Large Hadron Collider, or LHC. And it was the LHC, building right on top of this foundation, that would go on to discover the final missing piece of the standard model, the Higgs boson.
So Rubbia's Great Particle Hunt was a massive success. It gave us the most complete picture of reality we've ever had. But like all great science, it also opened up a whole new set of questions. The standard model is a triumph, for sure, but we know it's incomplete. It doesn't explain huge mysteries like dark matter or dark energy. So you could say Rubbia hoped to complete one incredible chapter of physics, which just leaves us all wondering, what comes next, and who's going to lead the next great hunt?